This is Krisztian Kordas from the Microelectronics Research Unit of the University of Oulu. Today, I will talk about low permittivity materials for applications at 6G frequencies. So we have witnessed the evolution of the cellular technology, and we are still in the middle of the development of the newest 6G telecommunication devices and networks. But how it started in some 40-50 years ago, when the first analog wireless mobile communication network was launched, could enable only simple phone calls, whereas soon after that, in the 90s, with the launch of the first digital networks, we could already send short messages and multimedia messages, and we could use our phones in roaming. With the turn of the millennium, we could already make video calls, and we could apply different types of internet utilities and could play with the smartphones. Today, with the presence of the 4G and 5G networks, we have a highly connected network of things called the Internet of Things. We have cloud-based devices, and we have applications that we could never dream about, let's say 20, 30 years ago. And now this development is being continued with the onset of AI applications, machine learning, and augmented reality. The key enabler of the development has been the increased frequency that we used in transmitters and receivers. But is it just so simple that we increase the frequency and then we have a faster communication rate and we have a wider broadband? Well, everything depends, of course, on software and hardware. And in this talk, I'm going to talk a little bit about the materials that we use in the hardware. And among those materials, I'm focusing on insulators, in particular dielectrics having very low permittivity. And I will show the point why these materials are very important and why the research in the field will play a role in the further development of 6G devices. So when we change the frequency of any telecommunication device, we have to do rescaling of device size. We have to change sometimes the component architecture, and we just need to change often the whole layout. And we have to consider also the physical and chemical properties of the materials that we use in the processes, so that actually we can eventually make the device itself. Very importantly, we have to keep in mind sustainability, cost efficiency, and the large-scale manufacturability of these components and devices. Why do we bother with dielectrics? What is the problem with them? Well, in any material that we place in electric field, the different charges of the material will interact with the electric field. And these interactions will cause polarization and result in certain permittivity, dielectric permittivity of the material. These polarization processes are depending on the frequency. Therefore, the dielectric properties of the materials are frequency dependent. Thus, simple scaling of the devices just to fulfill the demands of the increased frequency is not trivial. As I will show, different resonance processes that take place during the polarization modes result in absorption of electromagnetic waves and inherently cause losses of the energy. Apart from the absorption, we also see reflection losses that occur at interfaces of materials having different dielectric permittivity. So our goal is to minimize these losses and sometimes to reduce the dielectric permittivity of the materials. So what are these polarization processes? We have actually 4 major of these that we usually consider when selecting the materials. The type of interaction, how the external electric field is polarizing charges in a material, is highly frequency dependent. At very high frequencies in the optical regime, we find that electrons start moving according to the external field in reference to their nucleus. This is causing the so-called atomic electronic polarization. When we decrease the frequency to the terahertz regime, we find that covalently bound atoms in lattices as well as ions in ionic lattices move in reference to each other along the electrical field. At even lower frequencies, at the gigahertz range, we see that dipoles in the matter start to follow the electric field, so that as the electric field is oscillating, these dipoles are following the oscillation and rotate. At very low frequencies, we usually meet interfacial or space charge polarization, which is a simple drift of charged particles, typically ions, in the solid material at interfaces, resulting in different types of charge accumulations or space charges. So coming back to the 5 and 6G frequencies, we see that from these 4 processes, we still have the electronic polarization, the ionic polarization, and the dipole orientation present when we expose any material, any dielectric material to the electric field, the oscillating electric field. These polarizations will result in inherent losses, and therefore we have to do something with it to enable devices for these high frequency applications. And one approach is to replace existing materials with new ones that have either lower dipole moments or have lower polarizability, or just simply have a non-ionic character in the solid matter. Another, even more elegant way and more universal way of circumventing polarization is to get rid of materials from the solid. That is, instead of having bulk, we introduce voids in the matter, we introduce pores, and doing so, we obtain an effective medium whose dielectric permittivity will be changed. If the pores are filled with air, then we will decrease the permittivity. If the pores are filled with something else, a higher permittivity material than that of the original, then we will increase the permittivity. In our case, the strategy is to decrease the permittivity, so usually we introduce just simple tiny air pockets in the solid material. We can also add other phases, so the composite that we create can be not only binary mixture of things, but can be ternary, quaternary, and so on and so forth. So what can we solve with this? Having a lower permittivity, we can decrease the reflection losses, so we can decrease the Fresnel reflection at the interface. By removing material from the bulk, we can create voids, and therefore we can have a much lower attenuation of the electromagnetic wave in the effective medium, And all this will result in a higher intensity of transmitted waves. And thus we can improve energy efficiency and we can reduce the overall losses of any component. So in our laboratory we have been developing different processes and materials to enable low permittivity in the effective medium. I will show a few examples of those. In the first, we use very tiny polymer template beads with the size of below 1 micrometer that are acting as templates for our dielectric material. These polystyrene beads are chemically coated with a very thin layer of silica, silicon dioxide, thus forming a polymer core and a silica shell. After this coating process, we burn out the organic core from the core shell particle, leaving behind a hollow silicon nanosphere shell. But these are just simple separated particles. We cannot do much without modifying them further. So to have some sort of mechanical integrity of these very tiny hollow silica shells, we mix them with cellulose nanofibers, and by the interaction of the silica nanoshells with the cellulose nanofibers, we have some cohesion in the structure, and this material is acting like a Play-Doh. Having such, we can press it practically to any shape, and in this particular case we pressed it to slab, so that we can use this slab as a substrate material for high-frequency components. On the surface of this slab we evaporate metal micropatterns through a shadow mask and obtain a millimeter wave component, in this case the frequency filter. The next example is very similar to the one I have just explained, so that we start with the polymer template, coat it with silica, burn out the polymer core, but now instead of cellulose we use a polymer binder so that the particles are glued together and have even a better mechanical integrity than in the previous case. When we use, for instance, polymethyl methacrylate as a binder polymer, this polymer is a thermoplastic, so the composite itself is going to be a thermoplastic composite that can be hot pressed to virtually any shape, and in this case we demonstrated a bullet-shaped lens operating at very high frequencies. In the third approach, we start again from a template, in this case a polymer foam, a melamine foam, that we carbonize and then coat with silica again, and after burning out the carbon core we end up having a highly porous silica foam which has a very rough surface, so we have to coat it with cellulose film, and after this coating the structure is feasible for post-metallization, and as we have shown we can create different types of components operating again in the millimeter wave regime. So having these processes in our hand, we can form highly porous structures whose effective dielectric permittivity can be tuned down to values very close to the air. Virtually we have air in our hand, yet these materials can act as support of different types of functional structures. And having that said, we can show very high quality filters and lenses operating at 300 gigahertz frequencies. So in conclusions, we have shown that template-based synthesis routes are feasible for producing porous materials that we can then apply in high-frequency devices having very low permittivity and electric losses. These devices were demonstrated in filters and lenses at 300 gigahertz frequencies. And not only the low losses that we have shown caused by the very low absorption of this material, but the technology itself will pave the way for future new types of devices with graded index materials that will allow us to create fascinating 2D and 3D materials and devices with engineered gradient index and optical properties. Thank you.